We started to talk about the experimental tests, and the first one we're going to do, which I think I labeled B in the list, is deflection of light. So we've got the sun, the radius r. We've got a light beam coming in that would go like that if the sun weren't there. But in reality, gets bent by the sun. So this is the path it would have taken. And what we're going to calculate and what we're going to measure and compare is the angle by which the light ray is bent. So it comes in from infinity here, goes out to infinity here. So this we call, this angle, we call phi sub infinity. And this is the radial coordinate r. And if we draw a horizontal here, this is phi of r. And this R naught, I haven't drawn it perfectly well, but R naught is the point of closest approach to the sun as it goes past the sun. Whereas B is what's known as the impact parameter. That's at right angles to the line that would have been taken. So we've got our line element minus a dt squared plus b dr squared plus r squared d omega squared. And at infinity, so at r equals infinity, a of infinity equals b of infinity equals 1. That's the flat space result, a long way away from the sun. So you expect that it will travel, to start with, in a straight line way out here at constant velocity. So what you would say is that B is R sine phi minus phi infinity, which is approximately R phi minus phi infinity. And the velocity is approximately d by dt of r cosine phi minus phi infinity, which is approximately dr dt. And you can check that equations 13 and 14, let's just remind ourselves what equations 13 and 14 were from yesterday. A dr d phi squared plus j squared over r squared minus 1 over b equals minus e and ds squared equals minus e dp squared. Just check that those are the right ones. Actually, that's the one I want, which wasn't. I think I've got the wrong numbers. It's really 18 and 19. Yes. My mistake. $18 and $19 is r squared d phi dt equals jb and a over b squared dr dt squared. Plus j squared over r squared minus 1 over b is minus e, with e equals 0 for photons. Right, now we've got the right equations, we can check that they're satisfied when a equals b equals 1. So just to check consistency of the flat space when the sun isn't there, that everything's working as we think it should. Now we want to see what happens when the sun is there. Well, the first observation is that at the point of closest approach, dr d phi vanishes, And so we find J is R naught into 1 over B of R naught minus 1 to the half. Okay, now we need the other equation. Which was the equation for dr d phi yes. You recall from yesterday, a over r to the fourth dr d phi squared plus 1 over r squared minus 1 over j squared b is minus e over j squared. I think that was, in my notes, this is equation 29, but I'm not sure we went up to equations 29. Anyway, that's the equation we wrote yesterday. And if we look at r equal r naught, we find this. So that's fixed J, B, in terms of J. So we can now plug into the expression we had for phi, which I won't bother to write down again. And phi of r equals phi of infinity plus the integral from r to infinity, a to the 1/2 dr over r squared into 1 over r naught squared, 1 over b minus 1, 1 over b of r naught minus 1 to the minus 1, minus 1 over r squared to the half. Now, the change in phi as we go from r naught to infinity I'm sorry, as r goes from minus infinity to infinity. Is twice phi of r naught minus phi of infinity. So the deflection delta phi is this minus 2 pi. That's the amount by which the sun has bent the light ray. If that's greater than 0, it's towards the sun. And if it's less than 0, it's away from the sun. Now, gravity is attractive, so we'd be very surprised if it was away from the sun. And it isn't. So what is phi of r minus phi of infinity? Yes, that simplifies, doesn't it? So this gives phi of r minus phi of infinity equal to the integral from r to infinity dr a to the 1/2 over r over r naught squared into b over b minus 1 to the minus 1/2. Now we expand. Remember, m over r is small in our approximation. I'm using units in which g equals 1, by the way. So phi of r minus phi infinity is the integral from r to infinity dr r over r naught squared minus 1 to the half into 1 plus gamma m over r. I'm now substituting in the values of a and b in terms of the parameters beta and gamma. And you'll notice that beta has dropped out of the calculation. Which is a pity in a way, because it means we're testing less than we'd like to test, but that's the way it is. And this equals inverse sine r naught over r plus m over r naught into 1 plus gamma minus gamma square root 1 minus r naught over r squared minus square root r minus r naught over r plus r naught. So to first order in m over r naught, remember the celestial radius of the sun is about 3 kilometers. So m over r naught is pretty small. So it's a good approximation. Delta phi equals 4m r naught into 1 plus gamma over 2. So let's plug in the numbers. What we're calling big M is really G times M. We're ignoring the G, but the mass is 1.7 times 10 to the 33 grams. Weinberg seems to be mixing his units here. He's got the celestial radius in kilometers and the mass in grams, but okay. So that means M is 1.475 kilometers. And the radius of the sun is 6.95 times 10 to the 5 kilometers. So, as we said, that's a good, m over r is a small number. So what this means is that delta phi is about 1.75 I mean minutes or seconds? That's a second, isn't it? 1.75 seconds of arc times 1 plus gamma over 2. So quite small and difficult to measure. And as you can probably guess, or you probably read, the only time you can do the measurement is during a total eclipse. So you measure the starlight. You couldn't see the star otherwise. It was grazing the sun. You measure it where the apparent position of the star is us looking at the star. You compare the position of the star in the sky when the sun is there and when it's not, and you measure the angle. But when it's there, it has to be a total eclipse. And this was measured by Eddington in 1919. There's some dispute about whether he fiddled the numbers to make it work. But in any case, he got 1.98 plus or minus 0.16. And the latest is 1.007. This is 1 plus gamma over 2, plus or minus 0.009. And Einstein's theory, you remember, says gamma equals 1. So that's entirely consistent with Einstein's theory. And it's one of the results that made Einstein a household name and appeared in the New York Times and all that, and became an overnight sensation. They asked him what he would have done if it hadn't agreed with his theory, and he said, the theory's right, so I would have been sorry for the good Lord. Next one that he predicted was the perihelion precession of Mercury. So let's look at that one. And this was letter C, I believe. So we start with that equation here. And let's look at the setup. We've got the orbit of a planet, according to Kepler's laws, is an ellipse with the sun at the focus. The perihelion is the points where R reaches its minimum and maximum, perihelia and aphelia. So this is the perihelion. This is the aphelion. This has a Latin name, Semilatus rectum. And this distance is a into the square root of 1 minus e squared, where a is this distance, and this distance is e times a, and e is the eccentricity of the ellipse. So dr d phi vanishes at r minus and r plus. So we have that 1 over r plus minus squared minus 1 over j squared b of r plus minus is minus e over j squared. So we now solve for E and J. And we find that E is r plus squared over b of r plus minus r minus squared over b of r minus divided by r plus squared minus r minus squared. And j squared is 1 over b of r plus minus 1 over b of r minus over 1 over r plus squared minus 1 over r minus squared. Now, as R increases from its perihelion, the angle swept out is phi of R equal phi of R minus, where it started, plus the integral from R minus to R, a to the 1/2, 1 over j squared b of R minus e over j squared minus 1 over R squared to the 1/2 dr. But now we can plug in the expressions for E and J. And we find phi of R minus phi of R minus equals the integral from R minus to infinity, R minus squared into b to the minus 1 of R minus b to the minus 1 of R minus R plus squared into b to the minus 1 R minus b to the minus 1 of R plus minus 1 all divided by R plus squared, R minus squared into b to the minus 1 of R plus minus b to the minus 1 of R minus. Minus 1 over R squared, right. There we have it.
Why did the upper limit change from R to infinity?
I think I just made a mistake. Yeah, it should be R. Thank you very much. That should be R. Good. Now the total change in phi per revolution is twice phi of r plus minus phi of r minus. And if the orbit were a perfect ellipse, that would equal 2 pi. And the amount by which it's not an ellipse tells us that the Mercury is going around the Sun in this direction. The next time it comes round, the perihelion will have moved forward a little bit. And the next time it would move forward a little bit because it's not a perfect ellipse. So delta phi, the perihelion precession, is twice phi of r plus minus phi of r minus 2 pi.
Do you mean is okay in the expression in the integrand over there b minus 1 r is that in the numerator of that mark?
Yes, good. Thank you. Thank you. Now we plug in the A's and the B's and see what we get. And this time, it's going to depend on beta as well as gamma. So the bending of light was probing the value of gamma, but we'll now see that the perihelion precession of Mercury probes gamma and beta both. So to see that, let's plug in the values of A and B. A of R was 1 plus 2 gamma m over R. B of R was 1 minus 2m over R plus twice beta minus gamma m squared over R squared. So b to the minus 1 is 1 plus 2m over R plus twice 2 minus beta plus gamma m squared over R squared. Now, the argument of the square root in that expression there is R plus squared into 1 minus b to the minus 1 of R plus minus R minus squared to 1 minus b to the minus 1 of r minus over r plus r minus b to the minus 1 of r plus minus b to the minus 1 of r minus into 1 over r minus 1 over r 1 over r plus so phi of r minus phi of r minus is approximately 1 plus a half 2 minus beta plus gamma times m to 1 over r plus minus 1 over r minus times an integral that should be a plus r minus to r 1 plus gamma m over r into r squared 1 over r minus minus 1 over r 1 over r minus 1 over r plus to the half. So we're getting there.
In that big expression there, the integral, that is the power of negative a half or just a half? Or anything?
In this one here, should it be minus a half? Well, we'll check. According to Weinberg, yes. Why do you ask? Why do you doubt it?
I was just looking like at your expression above and trying to follow it through.
Did I miss out? Ah, good. Thank you. That should be minus upstairs. Good. Thank you very much. Okay, well, we're almost there, but we've got one more step. To do the integral, we introduce a new variable, which we call psi. where psi is defined by 1 over r equals a half, 1 over r plus 1 over r minus, plus a half, 1 over r plus minus 1 over r minus sine psi. And then phi of r minus phi of r minus if you do the integral is 1 plus a half into 2 minus beta plus gamma m 1 over r plus 1 over r minus psi plus pi upon 2 minus a half gamma m 1 over r plus minus 1 over r minus cosine psi. Now at aphelion, psi equals pi over 2. So this gives delta phi as 6 pi m over L into 2 minus beta plus gamma over 3. Now, the reason for writing a 6 here and a 3 here is that in Einstein's theory, this will be 3, I think. In Einstein's, no, that's not quite true, is it? Beta and gamma were 1. Why? Beta is 2? 2 gamma. Yes, good, that makes more sense. So the reason for writing that is because this, in Einstein's theory, this bracket will be equal to 1. And L, by the way, is you go back to our picture. So Einstein who has beta equals gamma equals 1, says delta phi is G is 6 pi m over L. And it's positive, so that means it's the advance, the perihelion advances. As you go around, it gets further. Now again, this is pretty small. Let me just tell you, by the way, by virtue for comparison, what Brans-Dicke theory would say. It has this parameter omega. So in the limit, omega goes to infinity. It agrees with Einstein, but disagrees otherwise, and experiment favors Einstein. Now, there's another way of saying this. You can ask how many revolutions does it have to do before it returns to its original position. So after n revolutions, which is n Mercury years, the perihelion will have advanced. N 6 pi m over L. Now for Mercury, actually, this is the fun part where you get to write that. Not sure how you... this is a zodiac sign. How does it go for Mercury? Weinberg uses it. Circle with a cross, yeah. Let's see. So the value of L for Mercury is 55.3 times 10 to the 6th. Or is it 5.53? I don't know why he writes 55.3 times 10 to the 6th rather than 5.53 times 10 to the 7th, but that's what he does. 55.3 times 10 to the 6th kilometers. GM, you remember, was 1.475 kilometers. So delta phi is 0.1038 seconds of arc per revolution. And Mercury, as I'm sure you all know, makes 415 revolutions per century. Per Earth century, that is. So delta phi is 43.0 seconds per century. Not a big effect, but we can measure it experimentally. So this is what Einstein says. An experiment has 43.11 plus or minus 0.45. So that means that 2 minus beta plus 2 gamma over 2 is 1, as we would hope, to within an error of 0.01. So again, it's consistent with Einstein's theory where beta and gamma are both equal to 1. And it goes one better than the bending of light because it's sensitive to both beta and gamma. Just to compare this number with other planets, Venus, Earth, Mars. This is 8 minutes. This is 4. This is 1. So it's significantly less for the others. So let's now do the next one in the list, which is radar echo delay, which is more recent. It wasn't one that Einstein proposed because he didn't think about it at the time. And here we're sending beams that bounce off a planet and bounce back to Earth again. And we calculate how long it takes, radar echo, and we find that because of the gravitational field there's a delay, which again is predicted by Einstein's theory. But it's rather, apparently, a messy experiment to perform, and it's hard to get a clean result. But the theory is clean, so let's look at that. This was number D in our list. So what's the setup? So we have the Earth going around the Sun. And then we have some inner planet, could be Mercury again. And we're going to look at sending a signal from Earth to Mercury. That's R1, R2, and back again, and seeing how long it takes for the return trip. So the total time to go from R1 to R2 is the time it takes to go from R to R0 plus the time it takes to go from R0 to R2. Now the difference is we're looking at time dependence in this particular test. So it's the dr dt equation that we're interested in. Just remember what that was. It was a over b squared dr dt squared plus j squared over r squared minus 1 over b equals minus e. And again, we're looking at light rays, so we can put that equal to 0. dr dt equals 0 at R0. So j squared is R0 squared over b of R0. It's sometimes useful to think of gravity as like going through a gravitational field is like going through glass with a different refractive index. So light slows down. One can think of gravity that way. So there's a delay from what you would expect if there were no sun. And we can calculate it. A over b dr dt squared plus R0 squared over R squared b to the minus 1 of R0 minus b to the minus 1 of R is equal to 0. So t of R to R0 is the integral from R0 to R. A of R b to the minus 1 of R over 1 minus b of R over b of R0 R0 over R squared all to the 1/2 dr. And I'll just quote you the result. This is a logarithm r plus the square root of r squared minus R0 squared over R0 plus m r minus R0 over r plus R0 to the half. Now this term is what you would expect if light traveled in a straight line. And these terms are adding to the time. So this is a delay. Radar echo delay, so it's called. And it's maximal when the ray just grazes the sun. So that's when R0 is the radius of the sun. And what you get, therefore, the final answer is delta T max. It's 4m into 1 plus gamma over 2. And once again, it's only sensitive to gamma. Log 4 radius of Mercury, radius of Sun, sorry, R0. No, not the radius. Radius of the Mercury orbit. That's an R0, I assume. That's the radius of the Earth, that's right. Radius of the Earth's orbit, which is a circle with a cross in it, I believe, over the radius of the Sun squared. Which is approximately 5.9 kilometers into 1 plus 11.2, 1 plus gamma over 2. And that will be in units where c equals 1. So that's when gamma, what we turns out to be the experiment, turns out to be 72 kilometers, which is 240 microseconds. And this says that gamma is 1.03 plus or minus 0.1. So it's not quite as accurate as the other tests. But it's consistent with Einstein's theory, as we would expect. And indeed, to date, all experiments on Einstein's theory are consistent with it. There's the issue of dark matter, of course. If Einstein's theory is correct, that means there's lots of matter out there in the universe that doesn't have the same interactions as the matter that we see in our universe. And some people are saying, well, maybe that we have to modify Einstein's theory. Maybe there's not the dark matter. But the conservative mainstream view is that there is dark matter, and Einstein's theory is just fine. Now we've got a couple more things to do, but that's a good place to stop for today. And next week we'll finish off the experimental tests. We'll say something about cosmology, and there may be a couple of days left to talk about something else that wasn't promised. We'll see what happens. So have a good weekend.